Welcome to Reconnecting with the Science. I'm Jim Walker. I'm a director and co-founder of the Climate Group. We are organisers of Climate Week NYC, of which this event forms one of the sessions. We have a room of people here at the New York Academy of Sciences in New York who are listening in, and we have an audience online. We're delighted that we're joined today by three of the coordinating lead authors on the recently released assessment report, first chapter, and we are going to hear from them in a minute. I'm going to introduce the three speakers. We have with us in Stockholm a sleepless group of scientists who I understand have been up for all of last night and have had late nights the last two nights with the final amendments to the report, so we're particularly pleased that they're able to join us today. So we have with us Professor Dennis L. Hartmann, who's the coordinating lead author on Chapter 2. He's a professor in the Department of Atmospheric Sciences at the University of Washington, a senior fellow and council member of the Joint Institute for the Study of Atmosphere and the Ocean. We also have Professor Nathan Bindoff, based in Australia, coordinating lead author on Chapter 10. He's Professor of Physical Oceanography at the University of Tasmania, a CSIRO Marine Research Laboratories, and Director of the Tasmanian Partnership for Advanced Computing and Project Leader of the Antarctic Cooperative Research Centre's Modelling Programme. And finally, we have Professor Jochem Marotzke, coordinating lead author on Chapter 9. He is Director at the Planck Institute for Meteorology and Vice Chair of the World Climate Research Programme. And we are delighted. Gentlemen, can I hand over to you in Stockholm to speak to our online audience and our audience in New York?
Thank you very much, Jim. I'm Nathan Bindoff. On my right here we have Dennis Hartmann, and on my left Jochem Marotzke. Yes, it has been a grueling 4 days. We started the plenary session on Monday to actually agree to the key document that comes out of the IPCC report, the summary for policymakers. It's fantastic news because 110 nations have actually agreed to this report, which is, I think it consists of 108 bullets and 22 pages and 18 headline statements. But of the total report, which is over 1 million words, we've really distilled it down to just 36,000 words. The key headlines are it's really that 110 nations have agreed that the Earth is changing, that it's unequivocal. And perhaps from my perspective, because I'm interested in attribution of human influences, those same 110 nations have actually agreed that the evidence for human influence on the climate system is clear. So what I'd like to do is, Dennis here will talk about the observations, I'll talk about the human influence on the climate system, and Jochem here will talk a little bit about the climate system and projections as well, and he will also touch on the hiatus. So if I could hand over to Dennis.
Thank you, Nathan, and good morning, everyone in New York. It's very nice to have this opportunity to speak with you about the work we've been doing for the past 4 years, in which we've managed to successfully translate through the delegates here in Stockholm. As Nathan said, I'm going to talk about the observational part, both from instruments, measurements, and also from paleoclimatic indicators, evidence from various natural recording systems. The overall statement about this observationally is the same as that was offered in AR4, which is that warming is unequivocal. And this is based on many independent lines of evidence, which I'm going to give you a few of the highlights of the observational evidence. First is the global averaged annual estimate of anomalies in the surface temperature over the atmosphere and the ocean. For the average over the past 3 decades, each of those has been warmer, progressively warmer than all the succeeding decades in the record, which go back to about 1850, back to 1880 with 3 independently produced data sets. If you employ the paleoclimatic evidence, then you can say that the 30-year period, the most recent 30-year period, is warmer than any that we have experienced in the last 1,400 years, where that longer time reference comes from natural recording systems like ice sheets and ocean cores, etc. The warming is also seen in the troposphere as well, the air above the surface as well as the surface itself. In the ocean, most of the heat, the energy increase in the climate system is occurring in the ocean. So we can also measure the increase in temperature with depth and therefore the taking up of additional heat by the climate system. In addition, we have, which is very well known, is the Arctic sea ice decline, which has accelerated in recent years but goes back to the beginning of the satellite record. Also, there's new evidence on ice sheet decline. For example, Greenland, we know, is losing ice at a rate in the last decade that's much greater, estimated to be much greater than in previous decades. So there's been a recent acceleration in the rate of ice loss from the continent of Greenland. Similarly, sea level is rising. Sea level has a huge impact on many people around the world. And the sea level has been increasing, and it's been increasing at a more rapid rate in recent years. And that rate is probably greater than any in the past 2 millennia. And between 1901 and 2010, the sea level rise has been approximately 0.2 of a meter. We can also measure with great precision the greenhouse gases in the atmosphere. For example, carbon dioxide, methane, nitrous oxide. Carbon dioxide concentration is 40% more than it was in the pre-industrial era. We can make a statement about the pre-industrial era because we have data on CO2, also nitrous oxide and methane from bubbles trapped in ice cores and other sorts of evidence that don't involve direct measurements. So in addition to being presently higher, 40% higher than it was in 1750, it's estimated from those ice cores that the CO2 concentration in the atmosphere is higher than it's been for the last 800,000 years. So that's kind of a very light summary of the observational evidence that warming is unequivocal based upon these multiple lines of evidence that I've related to you, and is statistically significant. Nathan can now talk about how we determine that those changes probably did not occur naturally but require a human cause. Nathan?
Thanks, Dennis. Yes, so Dennis has outlined a story of how the climate system has changed its state. You know, it's hotter, the glaciers and ice sheets are melting, and the oceans are warming, and in fact patterns of rainfall appear to be also changing. But the question really is, how is it that humans are doing this, and is it clear? Detection and attribution is all about trying to figure out the contributions that humans have made to the observed changing climate. And to do that, you need to understand what the internal variability of the climate system is. You need to understand what the natural forcings are, so whether there's volcanic eruptions, which can of course cool the planet, whether there's variations in solar radiation, and whether there's, for instance, other things that man puts into the atmosphere, aerosols. And these are all competing hypotheses, if you like. This is really about understanding the contribution humans did. So in our chapter we talk mainly about the contributions from greenhouse gas, the aerosols, the natural variations, which include solar variation and also volcanic eruptions, and internal variability. If you look at the surface temperature change of the Earth, for instance, since the 1950s we've come 0.6 degrees of warming, and of that 0.6 we've come to the conclusion actually that all of it can be explained by the combination of rising greenhouse gases and aerosols. both of which are, of course, human activities. So our estimate, our best estimate of that is 0.6 to 0.7 degrees of warming by human activity alone. So that's slightly greater than actually the observed change. Now, that's our best estimate, but the gold-plated standard that we require for IPCC related work is that we attribute a likelihood statement to the strength of this warming. And there are a few aspects that don't allow us to say absolutely that it's 100% man. What we can say is that more than half of that signal with a confidence level of 95%. So 95%, that's a 1 in 20 chance of actually being wrong. That's a 19 out of 20 chance of us being right. So it is very strong evidence for surface temperatures for man being the biggest contributor to the climate change signal that we've seen since 1950. In our business, we can't actually detect on a short time scale, and so I can say nothing around the 10 or 15 year time scale, for instance. One of the interesting things and new things since the fourth assessment report is that we've been able to, in our chapter, more clearly articulate the contribution of greenhouse gases by themselves. So normally you think of the observed change, 0.6 degrees. Now we have actually 0.5 to 1.3 degrees of warming contributed from the rising greenhouse gases that actually Dennis has just talked about. And we have from aerosols a negative contribution of about minus 0.6 to 0.1 degrees C. And they're the main two contributors to the observed change. A lot of people talk about the contributions from from solar and from natural variations like volcanic eruptions. And over the last 60 years, we're very confident that's actually less than plus or minus 0.1 degrees. And our best estimate of that is 0 degrees. And over that same period, from the use of models, which Jochem here can talk about more clearly, is that the best estimate of that also over the same period is 0 degrees. So there's a really quite convincing case that we weren't able to provide in the fourth assessment report around those human contributions to surface temperature change. But it's not all about surface temperature change. One of the things that's quite extraordinary from the fourth assessment report is actually how many other things we can attribute human influence to from the basis of the observations that Dennis here has talked about, and also from our understanding of the physics of the climate system. So, for instance, in the upper atmosphere and the lower troposphere, we're very confident of the cooling in the upper atmosphere and the warming in the lower atmosphere. We're very confident around the melt of Greenland and Antarctica. In the case of Antarctica, there's actually, we're slightly confounded in terms of being able to attribute the human influence, but in the case of Greenland, we're able to conclude that there's very likely to be an attributable signal from human influence. Sea ice is another component of the climate system, and Arctic sea ice, and the very rapid decrease in the Arctic sea ice over the last 30 years can be attributed to the human activity. The warming of the surface oceans, there are some very convincing literature, and our assessment around that is that it's virtually certain there's a detectable signal, and very likely there's a substantial contribution from the warming of the surface layers of the ocean in the upper 700 metres. There's actually evidence, surprisingly, that there's warming at depth below 3,000 metres, and this is also consistent with some aspects of our understanding of ocean circulation. And then finally, one of the things that I think is really nice about this report and working across all these disciplines is that we're able to connect together some aspects of the water cycle in a way that we would not otherwise be able to do. Ocean salinity is emerging as a very strong signal of changes in the rainfall pattern, and that changes in ocean salinity, which basically say where the surface of the ocean is salty, it's getting saltier over the last 50 years, and where the ocean is fresher, it's actually getting fresher over the last 50 years. And in the formal attribution process, what we find actually, this is exactly the signals that we expect from the from climate models of the last 30 years, last 50 to 30 years. The interesting thing is if you take the salinity information from the oceans, which we don't normally think about in terms of changes in precipitation, plus the fact that there's an increased amount of moisture in the atmosphere, evidence around changes in extremes in precipitation over land areas, and the rising precipitation that we can detect in the observations over the high latitudes. When you combine all of this information together, it's consistent, entirely consistent, and consistent with a signal of human influence, and we actually say that it's very likely that humans have been affecting the global water cycle. So it's actually from all of these strands of evidence, these multiple lines of evidence, that we conclude in our part of the chapter that humans are the dominant cause of changes in the climate system. Maybe I can hand over to Jochem here.
Well, thanks, Nathan, and good morning, New York City. I thought that I might talk about something which 3-4 years ago would have been a very esoteric part of climate science, but which somehow in the last 18 months or so has begun to grab headlines, and it is sort of what's sometimes called as the current climate cooling, or the warming slowdown, or the warming hiatus, and which may be a little surprising to show up when we've just talked about a big fat report which says the warming is unequivocal, and then suddenly we have the cooling there. And I thought by explaining you a little bit why we actually, as an IPCC team, really went so deep into the topic. It also explains you a little bit how IPCC works and maybe some of the strengths and failures. And it was in January this year when we met in Hobart for the last of our lead author meetings. So all the authors, all the 200 or so authors meet 4 times over 3 years, and this was our last meeting. And IPCC reports get reviewed, so we had gotten our reviews back of the last round of reviews, and we looked at the reviews and we realized, oh boy, there is something we are not doing that we should be doing. And it was exactly this fact that over the last 10 to 15 years, temperatures at the surface in the global average have been very high, but they have not risen further, or have only risen further by a little. And we got quite a few review comments in various chapters saying, what's going on? You need to assess what we know. And we realized that we are distributed in 14 chapters in the working group. Each of us is a coordinating lead author of one of the chapters. And we realized that pretty much every chapter was relying on some other chapter to take care of this particular issue of why it hadn't got so much warmer. And I think it was also true that everyone who thought someone else was doing it, everyone was thinking about a different chapter that should be doing it. So in the end there was quite a bit of a confusion, but what became clear is that we need to do something about it. It's a topic which is important, which has grabbed headlines, and we need to at least assess where we stand. And it went along with the notion that warming has stopped and the models all fail, and therefore the models are too warm, and therefore the models will be too warm in the future, and therefore we cannot believe the models at all. It's all a big lie. And so we were quite convinced that this notion wasn't quite accurate, but we turned out that no one had really good answers, and so we decided we form a team which is sort of across chapters. In the IPCC, it's typically put in, it's boxed in, it's put in a box, and so we decided we'd have a box. And we decided to put the box not where it logically should belong, but where people would expect to find it, which is in the chapter of model evaluation, which happened to be my chapter. And you could kind of see one of the weaknesses of IPCC. So we do things in chapters, and so sometimes things get lost sort of between chapters. But you could also see, starting in Hobart, one of the strengths of IPCC, that I just did the count. There are 14 chapters in our working group, and 7 out of the 14 chapters contributed lead authors who helped in getting answers on why are we watching this slowdown in surface warming. And it's been a thrilling experience, and I think we've come a long way in explaining things. So after that sort of little history, let me first define maybe what do we mean actually when we talk about the warming hiatus. If you look carefully, and Dennis and his people in his chapter, of course, they helped us in defining what are we talking about. We're actually not talking about cooling. We are talking about something that on the global average, the Earth's surface has not warmed as fast in the last 15 years as in the time before. So we still have warming over the last 15 years, but the warming is slower. That does not at all mean that warming has stopped, that global warming has stopped, because the ocean is still taking up heat, sea level is still rising, ice is still melting everywhere we look. So we're still in a warming world. It's just that at the surface that warming has slowed down. And by that time there were about 5 or 6 papers published. Every paper offered a different explanation, and every paper offered one explanation, and every explanation was different. So that didn't exactly help. What we managed to do was really bring it all together. And what we found is a few things where we are quite certain or quite confident, and a few other sources of confusion where we don't know what to do or what to think. One thing that surprised me no end is one reason why that warming is slower now has simply to do with the sunspot cycle, with that 11-year cycle that the sun sometimes is stronger, sometimes is weaker, and the sun happened to be particularly strong, or in a maximum in year 2000 and in a minimum in year 2009. And if you're looking at changes from 1998 to 2012, which is what we did, then of course you have that full downward turn of the solar strength just in your time series, which means the sun has a tendency of cooling, and it did. The other thing that we noticed is, again, I had to turn to another group to explain that to me, was that in the late 90s there were a number of small volcanoes went off, very obscure, hardly anyone knows their names, but they spewed enough aerosol into the stratosphere to have a discernible cooling effect. So what we had over the last 15 years is just that natural factors cooled the planet a little. And the other thing we are confident of, whenever you look at a 15-year period, which is very short in climatic time scales, you just have chaotic variability, chaotic in the mathematical sense that things just happen, things get colder, things get warmer sometimes, and we just happen to be in a phase where things get colder. So we have a good sense that there is some mixture of solar, volcanic influences, just some quirk of the last 15 years that led to what we are observing. There's still something we don't understand. If you ask the models, should you be able to reproduce that? The answer is, well, the way we simulate things in this particular setting, we would not expect the model to get a bit warmer or a bit colder at exactly the right time, but we would normally expect some models to get cold at the right time and others to get warmer at the right time, just by accident. Just that we looked at a lot of models. We looked at 114 different model simulations, and of these 114, all but 3 warmed by too much during that period. And we looked and looked and looked, and we dissected the models to the extent we could, and we have been unable to find a clear answer as to why they should be doing it. And so we are in a somewhat funny situation that we have a feeling we can somewhat explain what reality did in the last 15 years, but we have a much harder time explaining why the models
did not do a very good job overall during that period. And that's about where we had to leave it. So we try to put it all together. And there will be a lot of interesting research to be done. I'm sure of that. There's just one thing that we can say for sure, that unlike what many people would like to read into this, namely that models just respond too sensitively to carbon dioxide, that is the one answer we definitely know if it's correct at all, it can only contribute to tiny piece, but it could never explain why the models have been too warm. It's not that they generally respond too sensitively, it has to be something different. That we know.
Okay, Jochem, maybe we can hand back to Jim Walker and take some questions.
Thanks very much. Thanks very much for that, guys. We do have video contact with you now. We just got it the last couple of minutes, so we can see you in New York as well as hear you. That was great. Thank you for your input there. I think if I'm sort of just reflecting back on the key messages that we're seeing that observed warming is unequivocal, that we are becoming increasingly certain that this is human induced. So we have 95% now, so 19 in 20 certainty that this is the case. It looks like there are obviously some other observations that are now becoming more certain, and that obviously there's been a lot of media interest in the hiatus, so it's slowing down, but the sort of resulting conclusion from the process has been a slight downgrading of the sort of best case scenario for warming. Is that a fair assessment? You talked through the kind of the uncertainties and the links between the models, but if you were to sort of sum up in a nutshell, what's the sort of changing conclusion from that particular piece of work? Is that right?
No, it's actually on from that slowdown in the warming, one can actually not say anything at all about the long-term response to an increase in carbon dioxide. The time has just been too short to say much of that at all.
So the long time scale, since 1950 and longer, it's very much the same message, but the evidence is stronger. The trends are explainable and accountable using the combination of the models and the data, our understanding of the internal variability. So 95% certain, more than half, but our best estimates actually say that it's all human-induced for the last, since 1951.
So from an observational perspective, what we've seen in the last 15 years, we've seen before, in a sense, that a hiatus in warming is not that rare or uncommon. So the next decade perhaps will be very interesting to see what happens. If it continues to warm again, we'll probably be convinced that it was either some combination of natural variability or forcing from the sun or volcanoes. If it does stay level, I think we'll be able to do a much better job of assessing why. Turn to Jochem there. So it'll be a very interesting period for climate research, I think.
We're going to take some questions from the audience in the room here. Just while we get a microphone to people, I just wonder if you could just quickly reflect on the level of conservatism built into the IPCC process, which I think has again been something that's been of media and other interest over the last few weeks. So the last assessment report, the fourth assessment report, obviously had a huge amount of media interest, some of which was less than positive, and some sort of introspection there around how the results are communicated. Has that had an impact on sort of how you've been communicating the latest findings in the science?
So if I can talk to that, it has had an impact in the way we communicate. Let me just back up for a moment and summarise what sort of effort that goes into this report. It's for most of us, it's been 4 years of work. We've probably spent 25 to 30% of our time on it. There are just under 250 scientists, 239 I think is the precise number of scientists involved in this. We actually farm out a lot of the work to make sure that our results and assessments are rigorous. So there's another 600 contributing authors who are involved in that work. It's reviewed 3 times, as Jochem was talking about. In the case of the most recent meeting in Hobart, we respond to those criticisms and commentary that we get from both governments and scientific expert. I think across our report there were 55,000 comments, and eventually you'll be able to see those comments on the web. So we go to an enormous amount of trouble to make a very robust, rigorous assessment of the observations, the models, and our understanding of human drivers of the climate system, and in the process of attributing it to human activities. It's very rigorous, it's got to be authoritative. We're very conscious of the issues around errors that might occur and perhaps have occurred in other reports. The one around science is actually incredibly robust. I think it's a fantastic human endeavour, actually.
I would also answer this issue about the conservatism. I mean, when the AR4 came out, there was of course some high-profile criticism, like IPCC underestimates the climate change, and I had nothing to do with AR4, so I was a complete outsider. But I would say that one of the papers that came out almost the same day as the IPCC report came out and claimed that IPCC vastly underestimates sea level rise, that paper has been taken apart so clearly by the current generation of IPCC report. It just showed that this paper had no basis, no scientific basis, or a very weak one at best. And so it's been a very successful paper if we count citations, but I have the impression that mostly people showed that this paper was wrong. And so and that shows what happens if one tries to be ultra nimble in research. What may easily happen that the latest paper that comes out is seen as the best. This must have brought us most strongly forward. But then the real proof comes if this paper is subject to scrutiny by people who test the methods, extend them, and so on. And often you just find that paper which appeared so wonderful really wasn't so great after all. And I think that's one of the great strengths of IPCC, that it doesn't respond to these sort of jittery thingy single papers, but there has to be a whole body of evidence before it gets prominence in IPCC. And actually I think this perceived conservatism is a great strength because it lends robustness to what you find there.
That's great. Can I switch to some questions from the room just to give some of our audience a chance to answer? Can you identify yourself and briefly beforehand?
Absolutely. My name is Clara Vondrich. I'm the Director for Climate and Energy at Fenton Communications. Thank you so much for a truly excellent summary, particularly impressive given that you guys have gotten about, a few hours of sleep over 3 nights. I've heard a lot of the top line findings through various leaked documents in the past few weeks, but the one I didn't know was this impact on the hydrologic cycle, which was really interesting to learn about, and I want to dig in more. Also wanted to commend you for your flexibility as this giant body for being able to respond to this faux pause, as my friend Joe Rome calls it. It's really something that I think has the potential to really derail the conversation right now at precisely the time when we have very little time, as the IEA has said, to shift course and start ramping down emissions. My question has to do with, I have 2 actually. The first is, you've noted that global surface temperatures have risen by 0.6 degrees since 1950. I wanted to ask about the period before 1950, namely the period between the start of industrialization through 1950, because my latest understanding is that net warming since beginning of industrialization has been more on the order of 0.8 to 0.9 degrees Celsius. Second question is, I wanted you to address another one of the theories regarding the slowdown, which is that the deep oceans, that the heat has been trapped by the deep oceans, that 90% of excess heat actually goes to the oceans. And I understand that Kevin Trenberth has put out a paper, and it may be too recent for you guys to have addressed, but did want to hear your comment on that. Thank you.
Let me start by addressing the question on temperature change. One of the things that impressed me about this IPCC was that we've moved away from an emphasis on whether it's warming or not to a question about how much it has warmed. So the observations group on global mean surface temperature has three independently produced estimates of global mean temperature back to 1880, which is, however you define it, not the beginning of the Industrial Revolution. And there's one record that goes back to 1850. So the question is, how do we quantify the difference between some period when humans didn't have an influence on the climate and now? And in this document we've produced two numbers. One is a linear trend between 1880 and the present, which is the period for which we have three data sets, and the other is a difference between the average between 1850 and 1900 and the last decade from 2003 to 2012. Those two numbers are roughly the same, about 0.8 within the uncertainty. So that's a number of increasing interest to people, which unfortunately we don't have any instrumental evidence prior to 1850, and the first 30 years of the record are only based on one data set for which we know the global sampling's rather poor. Somebody want to take the...
I'll talk to the deep ocean and the change of the state of the climate system. So you're quite right. Kevin Trembus did publish an article. He was a second author. It was Balmaceda et al. And that paper did discuss a possible kind of reconfiguration of the ocean. And that sort of reconfiguration is often seen in the numerical models of long simulations. One of the tantalizing things, though, is actually the upper ocean has warmed up. That's completely clear and obvious. But one of the nice new results, and we only just have enough data, to kind of tantalize us or tease us with the idea that the deep part of the Southern Ocean in particular is warming up. And just recently, one of the results in the report is that we're very certain that the surface waters have warmed up, top 700 metres. But there's a the surface to 2,000 metres is still warming up. And then below 2,000 to 3,000, there's no change. And then below 3,000 metres, there is, in the Southern Ocean, a relatively rapid warming. And that relatively rapid warming is big enough to actually explain the energy budget, which we've for the Earth, and it's a way of actually storing excess energy. And there are features like that are actually in the numerical models and simulations. So while we don't have quite enough information to close the case and really confirm the Balmaceda paper, it's tantalizing, and it's starting to draw us in and start to offer the sorts of explanations we need around these variations in surface temperature and in the Earth system.
We've got time for just one more quick question before we close the webinar section. Thank you.
Hi, I'm Jeff Masters with Weather Underground. Thank you very much for your hard work. It's greatly appreciated. In December, NOAA's National Climate Assessment published a sea level rise estimate, with the upper end being 2 meters for a worst case scenario. So can you talk to why the two assessments came up with different numbers for their top end sea level rise? Yours was just under 1 meter.
I think it's there's a certain class of models which tend to come up with that high number, but it is unfortunately tends to be that class of models which has been quite thoroughly discredited through the also through the chapter now that looks at how models of sea level rise should work, and really those models that have the mechanisms in. And now, maybe in fairness, one should say that no one can completely exclude that there would be sea level rise between 1 and 2 meters. It's just so very unlikely that that our colleagues from the sea level rise chapters felt that they really should not include that number. But if you're willing to push every possible mechanism to the extreme, you can just barely get 2 meters in a century. But I guess most people there in that chapter felt, and I would have felt along with them if I had been a member of that chapter, that this 1 meter of sea level rise as the upper end or as the upper likely range for 2100 was really a good number to put in there.
So just to add a little bit to this story, in the fourth assessment report, we projected about 81 centimetres when you took into account ice sheet contributions. In fact, it turns out a completely different set of people, very careful analysis of processes around sea level, and they've come up with almost the same number. And what I think is going on here is that there's a very considered and analysis, because all of it's in the literature, of the contributions from all of the components, from Greenland, from glaciers, from Antarctica, from the increase in temperature in the oceans, and also the response of the Earth to those changes in mass of Greenland and Antarctica, because they actually contribute to sea level, and as a consequence not everywhere will actually rise. But that considered response has actually provided exactly the same answer that we had in the fourth assessment report. So I think that's a very solid result that's come out of this analysis.
That's great, thank you. I'm afraid that's all we have time for on this particular section. I'd like to, the room will join me in thanking the three speakers, Professor Dennis Hartmann, Professor Bindoff, Professor Marotzke. Not only for joining us after several sleepless nights, but also for your efforts over your careers in the last few years in taking part in this mammoth assessment process. I think we really appreciate the ability to have this summary of the science. I also just want to quickly say thank you, as I didn't have a chance at the beginning, to UN Foundation and to the New York Academy of Sciences, our partners on this webinar. Gentlemen, I hope you sleep well and safe travels on your way home.
Thank you very much.
Thank you.
Thank you. Thank you.